Hello everyone, welcome back. Welcome back to Business Intelligence. I know for the past week it has been difficult for everybody. Everybody's situation is different, but we all have been hit hard and negatively in fact impacted by the COVID-19 outbreak. I want you to know that as much as it's difficult for you to stay focused and study everything that you are supposed to study, it has been hard for me to stay focused. I have a young kid. The school system is out, so besides preparing for the class and doing my other work, including research and other services for the university and for the department, I also have to allocate additional time to make sure my child is educated and his progress is not lagging behind. So it has been difficult. But I know that it has been difficult for you, for every one of you, for you guys. So I think it's that time of the life. This is unprecedented time. It's once in a lifetime situation. It is in this time that we demonstrate that we can do it. We're strong. And better yet, it's time to demonstrate the strength to help other people, to help our friends, to help our family, to help my students, and to help your classmate and fellow students who have been feeling weak and helpless, and we can all feel it. It's time for us to demonstrate the strength and to showcase them. And this is contagious. This strength, human strength, is contagious. Your strength can affect other people feeling weakness, and even if you may not notice, your strength will help them become stronger. They can feel it by seeing that you are strong. So keep doing it and keep being strong. I hope this message helps everyone to feel the strength, and together we can do it. Now, this video is going to continue to talk about neural network model. Now, previously, in the previous video in last week, I talked about the high level of neural networks. And you can see that a typical shape of the neural network that we will be talking about is on the screen. And it's important to know the basic structure of the neural network model. And just to reiterate and repeat the fundamentals. Let me change this to a highlighter, or a laser point. So this is the basic structure of a neural network that we are interested in this course, and several key concepts. This neural network is the kind of neural network that is described as multi-layered, 1 layer, 2 layer, 3 layers, and 4 layers, 4th layers. Multi-layered feed forward, in which case the flow of information always go from the left to the right. As you can see, all the arrows are pointing to the right. So I typically describe these layers to be the upstream layers, and these layers are the downstream layers, just like how water flows through a creek, and it flows from the left to the right. So the left hand side are the upstream layers, and the right hand side are the downstream layers. And also fully connected. This neural network is fully connected, where each of the upstream layer, the immediate, let's use this layer as the focal layer, and the upstream layer, the immediate upstream layer is this layer, the input layer. Fully connected means that each of the node of the immediate upstream layer, that would be these nodes, each of these nodes are fully connected, are connected to each and every node of the immediate downstream layer, which is this layer. As you can see, this input node or input neuron is connected to this hidden neuron, this hidden neuron, this hidden neuron, and that hidden neuron, 4 of them, as well as all of the other input neurons. Each of them are fully connected to each of the hidden neurons in the first hidden layer, not to the second hidden layer. In the kind of network, neural networks that we are focused on, it is not. There is no skipped layer. There is no direct connection between layers that have a gap inside. And also fully connected means that each of the hidden neurons in the first hidden layer, each of these 4, are fully, entirely connected with each of the hidden neurons in the second hidden layer. Right. And what does it do, mean, really, fully connected? It really means that each of these lines with arrows on it represent a coefficient. And typically, no, I need a pen, and let's take a blue. Each of these lines, each of these represents a beta coefficient, and this beta coefficient is going to be estimated and calculated during the model training process. Although there is really no boundary, this beta realistically, hypothetically, there is no boundary for this, for each of these beta coefficients that represents the connections, the lines here, similar to regression lines. But really, its realistic boundary is typically bounded between it's typically bounded between -1 and +1, and typically a fair amount of these coefficients tend to be very close to 0. This is the way that neural networks are able to selectively emphasize some of the information and suppress some of the other information, or by suppressing the information, it really means that neural networks has decided during the training process that those tend not to be helpful in predicting the output. So that's why the estimated betas for those non-predictive sort of patterns or variances from the model are assigned a value very close to 0 so that those variances will not affect the prediction of the outcome, in order to make sure that the prediction accuracy is higher. Okay, so to recap, this kind of neural network is called multi-layered feed-forward from left to right, fully connected or completely connected neural network structure. We typically call them, or data scientists typically call them, fully connected net. Now the second key point is forward propagation. And forward propagation is very akin to say that the neural network is feed forward, where the information flows from left to right. And what forward propagation really does is in simulating a decision or simulating a decision-making process, and use the coefficients and the input variables to calculate the predicted outcome. So that's what forward propagation really do. It makes use of the current value, even in the middle of even if it's in the middle of training. It uses the input values of the values of the input data and the estimated values of beta in the current step to iteratively calculate the values of all the hidden nodes as well as the outcome neuron in the output layer, and simulate the predicted outcome. So that's really what the forward propagation is doing. Now, I also talked about, in the previous video, I talked about back propagation. Now you might have a question. So the neural network, I said the neural network is forward feeding, it has a forward propagation. Then why does it need a back propagation? Now you need to remember that back propagation doesn't mean that information in terms of a decision-making process, information can flow backward from the outcome to the input. It doesn't mean that. Back propagation is needed because the model has to go through training process, and all the coefficients, including both beta, and there's another type of coefficient here is the biases. Together they make up all the coefficients in the neural network. In order to optimize the values and to improve the model, these values, the values of the coefficients will have to be updated. But the way that they get signals regarding how to update these values will come from the errors. And where does the error come from? The error is the difference between outcome and output. Outcome and output. Let me clear that. Now, what is outcome? Outcome is the y value. What is output? Output is the predicted likelihood of the outcome. And the difference, difference between outcome Y and output, the simulated output, is the error. And this error needs to be fed backward all the way through this network and distributed. The feedback needs to be fed back and properly distributed onto each of the coefficients here, so that they will know how they should be updated in order to get closer to a better model. So that's what the back propagation or backward propagation is really doing. That's the purpose. It doesn't mean that information can flow from the right to the left. The back propagation only exists in the training. This one only in training process. Suppose that you have trained a model. The model has attained a reasonable performance level, and you are using this neural network model to make predictions using out-of-sample data set, the real data in real production. In that case, you would almost, unless you decided to retrain the model, you would almost never use any backpropagation again. You would your computation process would almost never enact any of the backpropagation process. The only process that is being enacted is where you have the out-of-sample data feed in by using the trained model. By trained model, it really means a long list of betas and the biases. Input data go through a linear transformation process, a summation of the multiplication between the beta coefficients and the input data, get the linear summation of the values, go through the nonlinear activation process, and then go to the next step, go through another round of linear combination and activation process, and on and on and on, go through all the layers, and ultimately produce a likelihood estimate for the outcome, which is then translated to the predicted outcome. That's a feed forward. That's a forward propagation process, for an entire new data set. And in the end, you have the predicted outcome for all the cases in the out-of-sample data set. And that's it. That's a production process, which only involves the forward propagation, not the back propagation. The back propagation is only used in the training process. And for key terms, I guess that's it. And also, just a side note, you probably will notice that, in this graph, this neural network has a relatively large input layer. Hold on. Input layer. And has a somewhat smaller first hidden layer. Hidden layer 1. And a slightly smaller hidden layer 2. And in the output layer, there's only one one node. So, you know, you have these fully connected, and here it's fully connected. So it's somewhat like it's a triangle shape. It's a triangle shape put sideway. You know, it's like sleeping on the side. It's a triangle, which is like, you know, a triangle, and put it sideway, and information flows this way. I wouldn't say for all the neural networks that will look similar to this, but for those neural networks that are fully connected, you know, fully connected net or completely connected feed-forward neural networks, it will almost always look like this. Even if it does have, you know, hundreds of hidden layers, the input layer tend to be very large, because in some cases there is a huge data set to be learned, and as it goes through, as the neural network flows through different layers, the layers become smaller, and when it gets to the output layer, or output nodes, the number of neurons become smaller and smaller. And this is a good design, because the purpose of the model is to extract patterns. It's not supposed to contain everything in the data set, and that's not the design. And in terms of data set, there are information as well as noises in the data set. So the data set contains a lot of variances, including information and noises. And the neural network is like a sift that tries to extract more and more abstract data or abstract information from the data set, so that in the end it becomes a very, you know, concentrated pattern simulating formula to only apply predictions on really concrete patterns being extracted. So that's why typically you have a sideway triangular shape of neural network, where the input layer tend to be the fat base, and the output layer, output neuron, occupies the upper, you know, the upper corner of the triangle. So that's how things typically are. And I think, you know, for neural network, it's a really complex model, and for this class, because it's an intro to data mining and predictive modeling course, I don't require you to understand several aspects of the really technical facts, including the backward propagation. You know, the forward propagation is quite intuitive. You know, you apply the formula and calculate the linear combination and the nonlinear activation function, and that's mostly it, and it goes through several layers. But the backward propagation is what really is the technical parts of the model, and I will skip that. If you're interested in at least, you know, uncovering, you know, revealing the inside process of the back propagation, I would suggest that you can follow the book. And these slides, the second portion of the slides, are from the LaRose textbook, and it simply highlights the key points in the example in textbook, where it goes through the detailed calculations of one example by using a set of random initial coefficients, and by step shows you how to allow the error, the error that I talked about, the error in the output layer, to allow the error to propagate through the network backward from the outlier to the hidden layers, and all the way up to the first hidden layer, and to where the first coefficients are that connects the input layer to the first hidden layer, and how those coefficients will update each other by using the feedback learned from the error. So that's the essence of the backward propagation process, and it uses a gradient descent technique to calculate and to distribute the amount of feedback across the different hidden hidden nodes and the coefficients. So I will skip the technical part. If you're interested, feel free to read the book. And there are several other technical topics which I will skip for this course, but feel free to read about them. They are something called learning rate. Eta is learning rate, and there is a momentum. These two are fairly technical topics. More advanced neural networks will use momentum. Not every fully connected net will use momentum, but learning rate is implemented in almost every neural networks, including the fully connected and those advanced deep neural networks. So I'll not talk about those, and the homework as well as the exam will not require you to do any exercise about those. But if you're interested, feel free to read the book or look at the slides to follow the book, and ask me any questions if you do have. With that said, there are a few quick reminders here about doing neural networks. Let's see. And the first thing is about transformations and standardizations. Variables will need to be standardized, and as I said, range standardization would be the preferred. Range standardization is the preferred method for neural networks, but standard deviation typically will not produce results that are drastically different, because both of them do standardize the variables in certain way. It's just the different flavors. So this has to be done, and for any other obvious data problems, they need to be fixed, including missing values, erroneous values. Of course, missing values lead to less information to be learned. Erroneous values will tend to introduce biases into the model. But in terms of skewed distribution, it's really difficult to say one way or the other. Does skewed distribution always cause trouble to neural networks? Not always, but it certainly could. My suggestion would, because of all the difficulties in knowing what really will happen, the judgment has to be made really case by case. And as I said, I would suggest that you do both versions, keep everything else the same, and see for a specific problem that you're dealing with, does fixing the skew distribution really help increase the neural network model's predictive power. So that is really a case-by-case judgment to be made. And finally, input variable selections. So you could throw in a large data set with hundreds of inputs and hopefully, allow the model to learn and to be able to select, which input variables tend to be more predictive of the outcome versus others. But as you increase the number of input variables, the time for learning for the neural network model will increase, because the way that the neural networks improve itself and optimize the coefficients, the process is so complex, the calculations are so nonlinear, the optimization process is not linear, to the extent that it will dramatically slow down the conversion, the process that the neural network model learns its optimal coefficients. So if there is obvious conclusions to be made about certain variables not having obvious values, then it might be worthwhile to go through some kind of input selection process to limit the scope of the input data. That said, there's always a however here. If you do have a large data set, if you do also have sufficient computation power, then selecting input variables a priori, which means selecting input variables before you start training the neural network, is not advised, because if you do have those resources available, it is indeed worthwhile to allow the computers to allow the neural network model to be able to surface important signals from the input data. So that's my suggestion. Okay, so next, let's do some hands-on. Yay! All right, let's do the hands-on. So for today's hands-on, since it's been a little while before I did some real-time hands-on demonstrations, I have decided to do a lengthier demonstration so that you can follow along again, and in the meantime practice how to train a neural network model. For this hands-on demonstration, I will start a new project. I will generally follow along the steps that are included in this tutorial, but instead of using the data set that this PDF tutorial uses, I will instead use the data set that is used in most of the other chapter by chapter demonstration tutorials by SAS. So the specific data set I will use is the PVA97NK, which is one of the data set used for competitions in the past. A little bit of a heads up about neural network model. I will, because the project setup process might be long, I will fast forward most of these steps in the video, but you can feel free to slow down, use slow motion of the video to view some of the specific steps. I also did a little bit of cuts to remove part of the video that was that I did wrong or I revised to sort of keep the video flow smoothly. But there is one thing I would like to bring up ahead of time, which is the standardization procedure, which is part of the transformation step. You can, as you know, you can use the transform data node to do a list of things. You can use that node to normalize or to standardize the variables so that every variable will have the same scale or the same mean and same standard deviation by using the z-score standardization. Or you can make sure every variable has a 0 to 1 range by using the range or min-max standardization technique. However, for neural network model, it is not necessary to do standardization in extra to prepare the data set for the model, because the neural network model, the model node in SAS Enterprise Minder has a built-in characteristic, a built-in property that you can select to automatically standardize the variables for you, and you can select from a short list of options. So from there, essentially, you can include the variable standardization process without having to do it ahead of time explicitly in the process. So in the fast forward video portion that you see before the point of using training the neural network model, I did not do the standardization procedure for neural network model, but this is only for neural network model training. You should understand that for those models that require that depend on the way that you standardize the variables, standardization is still required. And for those models, the node does not have variable standardization procedure built in. And those models include k nearest neighbor. Two models that we have talked about so far that whose performance depend on or will be biased if the variables are not standardized. And those two models are k nearest neighbor and neural network model. And neural network model node in SAS Enterprise Minder have the internal capability to do standardization, so you don't have to do it beforehand. But for k nearest neighbor model, you will need to explicitly standardize the variables before you feed the data into the model. Otherwise, the model will be severely biased because of the different scales of the different variables. Okay, now I will start this project from the very beginning. Okay, now we have done all the preparations. I have skipped the exploratory data analysis, but you guys all understand that for any new project dealing with new data set, a fair amount of exploratory data analysis is required, since I'm familiar with this data set, and this is mostly for demo purposes. I skipped those parts, but you guys have good understanding of why you need to do the due diligence in exploratory data analysis in order to do the project well. Okay, now I'm going to demonstrate how to train a model of neural networks. I will train the neural network model first, and then I will also train a decision tree model and use a model comparison to compare the two models. Now, for this problem, because this data set is about donation behavior, and the target variable here is a binary variable. That means yes or no, two discrete labels, binary variables. So this is a classic binary classification problem. It's a supervised learning project. So obviously, without specifying the decision weights, the best criteria for comparing and selecting the best models would be the misclassification rate, calculated based on the validation data set, because I have the data partition node built into the project. Okay, neural network. I will do a classic neural network model. Now, first find the model node. It looks like a triangular shape put on the sideway. You know, the fat base is on the left, and the pointy triangle corner head will be on the right. Alright, that's the neural network model. And a few important things to specify the first moment that you drag and connect the path to a neural network model. And my magnifier here. Okay. The first thing to note is the optimization part. Let's see. Let's click open the optimization. So this dialog allows you to specify mostly the technical properties of the neural network model training process. Training technique uses default, that would be fine. Maximum iterations. Now each iteration is the forward and backward propagation one time, and with each iteration the model will be improved. Model parameters will be optimized for one round. One round is rarely sufficient, so you need multiple rounds. With each additional round of iteration or model training, the model tries to reduce the error rate. It becomes what we say complex, because the model parameters are being pushed toward what the model thinks that better captures the trend in the data set. The model becomes complex. Even though the structure didn't change, the parameters, whatever that needs to be non-zero, becomes closer to the value that the model design desires the value to be. So literally it's becoming more complex. And typically 50 is not sufficient. 50 would be sufficient to get the best model, but may not be sufficient to see the overfitting chart. So I suggest for a data set as big as 10,000, I would suggest you pick a bigger number, so 100 or 150. But you should know that as you increase this number, training time will increase. So you also have an option to put a cap on the total number of hours be trained. With today's laptops, with Intel Core i5 or above, you rarely will need 4 hours to do the 100 iterations of training, but just in case. Nonlinear options use use defaults, use preliminary training. Let's turn it off as the tutorial has said, and let's do a complete training from start. And although that is more technical, here the network side is more relevant configurations about the structure of the neural network, and this is most of the design characteristics of the neural network. Multi-layer perceptron would be the default. You also have the option to do a few different things. For the purpose of this course, we'll mostly do the multi-layer perceptron. And here, direct connection would be the connection that skips a layer, and we won't do this here. Number of hidden units. This is a key configuration variable. 3 means you want 3 hidden nodes in the hidden layer, and to be clear, in SAS Enterprise Minor, the neural network models only allow one hidden layer. So this would be it. This would be the number of hidden units that you have in the only one hidden layer. For this data set, I would change to something like 6. And there is a critical note here. Now, input standardization. Because we chose the default multi-layer perceptron, the input standardization option of using z-score standardization is fixed. Sometimes you have an option to change that. Input standardization. Specify the method that's used to standardize the input into your user-defined network. Standard deviation is a default. Sometimes you do have the option to change that, and let's see what will allow you to change this standardization. But even if you use standard deviation, it won't be too much of a difference. So this is where I said, because variable standardization is so critical to the successful training of neural networks, it has a built-in function so that you don't have to have an extra, a variable standardization node explicitly built into the path in the process, in the preparation process. Okay, so that is good. And model selection criterion. This is where the best model is selected based on what the criteria based on which the best model is selected. As I said, the problem is binary classification, so the misclassification will be used to select the best model. And things in the score is whether or not you want the model to calculate when it when the model is applied to out of sample data set. This would be the implementation phase. Okay, so only a few properties to change, but that really is what you need to train a neural network at this stage. And you should be ready to train to run the model. So how do you interpret the results when you have trained a neural network model? Don't look at these graphs for now. Let me talk about a few things that you need to do in order to answer the questions in the homework. Homework 6 about neural network hands-on problem. And the question first asks you about the topology of the network. And to answer that question, you need to know two things. What are the layers in the neural network, and how many neurons are in each of those layers in the network? There are 3 layers in your network. That will be typical. That will be almost always the case in this course for the neural network models that you train. There is an input, the fattest layer, input layer. There will be a hidden layer. There will be only one hidden layer, and there will be an output layer. As it goes through the 3 layers, it becomes thinner and thinner, smaller and smaller. And second part of that question is how many neurons are in each of those 3 layers. The number of neurons in the input layer depends on the size of the input variable, depends on the number of input variables and the levels of those input variables. There is not a very easy way to figure those out simply by looking at the input variables in your data set, because as you go through the data preparation stage, you have transformed some of the variables, you have imputed some of the variables, which created new variables and replaced old variables. Also, some indicator variables have been created for those that have missing values. So it's not very easy to figure out the number of input neurons from the list of input variables, but there is a good way to find that out in the neural network output window here, and I'll talk about that. For the rest of the layers, it's more straightforward to figure out the answer. How many neurons are in the hidden layer? That is the specification that you chose. Recall that in the network dialog, I changed the number of hidden units to 6. That is the size of the hidden layer, which corresponds to the number of hidden units. To answer how many neurons are in the output layer, it depends on the type of target variable. If the target variable is a binary target variable, then there is one and only one output neuron in the output layer, because you only need to have one metric, which is the probability that a case is predicted to be one class versus the other class. So you only need one neuron in the output layer. But if there are more than two discrete labels in the target variable, and if the target variable is nominal with more than two discrete labels, then you need as many output neurons in the output layer as there are discrete labels. So if there are 3 discrete labels in the target variable, you need 3 output neuron in the output layer. So those 2 layers would be easier, would be more straightforward to figure out without even looking at the result. Now let me show you how to find out about the number of input neurons in the input layer. Now, inside the results output for the neural network model, there are a lot of information here. There are a lot of results here because a neural network model is fairly complex. It has a lot of coefficients, has a lot of parameters to be estimated because of all those fully connected connections. And the part that you need to look at, there are 2 parts that convey essentially the same information in terms of the number of input, a number of parameters, but the results are different because one is the initial value and the other is the estimated value. And as soon as you see a long list of variables here, it says the neural procedure optimization start. This is the starting point where the algorithm randomly pick values close to 0. As you can see, these values are fairly close to 0 as a starting point, because the algorithm has to start from somewhere, and the best starting point would be the random values that's fairly small. And you scroll to the bottom, you see a very large number here. This list has 199 parameters here, and if you keep, there's some model performance metrics here, and if you keep scrolling, you'll see another table that looks very similar to the table that you just saw, but now you see that the estimates are the estimates, they are the optimization estimates. They are not random estimates or random numbers. These are the estimated parameter values. And if you scroll to the bottom, you also see 199. That is the total number of parameters being estimated. And if you keep scrolling down, there are additional outputs. Now, so here the question is how to figure out the number of input neurons in the input layer. The first information you need to know is how many hidden neurons did you specify for the network, because this directly affects how many arrows did each of the input neuron point out of into the downstream hidden layer. If you have 6, if in this case I had 6 hidden neurons, I would have 6 arrows pointing from one of the many input neurons each to one of the hidden unit of the hidden layer. So this will affect your calculation of the number of input neurons. Because the number of hidden neurons is 6, as you can observe here, as I scroll down, you see hidden layer first unit. This is the coefficient that the input variable dem median, demographic median home value points to the first hidden unit of the hidden layer. And as you scroll down, you can see different input neurons or different input variables pointing to the same hidden neuron. And at some point, you'll see a switch to 2, the second hidden neuron. And if you keep scrolling, you see the number rotating from 1, 2, and to 3, 4, and 5, 6. And at the last, before and after the last coefficient that points to the 6th hidden neuron, it rotates back. It's somehow restarted. This is because the type of variable have changed from one type to another type. Observe that all the variables before, including 120, are interval variables, but beginning the dem homeowner, this is the binary variable, and so it will for every hidden neuron, it will be connected with every binary variable before it restart the counting again. So after only a few number of coefficients for the binary input, is there you start the coefficients for the nominals, and then it will finish. So the key to count, and before I talk about the next step, you up till this point, you see that these 6 terms as the bias. These are the bias terms that go along with the hidden neurons linear combination function, and these are not because of the input neurons, but because of the hidden neurons. So you don't have to include these numbers in the calculation. And for the target, for the for the output, output layer, the output neuron, because there's only one output neuron, it has to be connected to each and every one of the hidden unit. So it has 6 coefficients together with the bias. Okay, so all of these you don't need to include in the calculation. And here, the number that you really need is the number that indicates the last variable, input variable coefficient with the last hidden unit. This is the 6th hidden unit. Now, so what are all the above? These are the coefficients that connects all the input to all the hidden units. Because there are 6 hidden units, you only need to use this number and divide this number by 6. Look at the results here show up on the screen. 100 and 186 divided by 6, because there are 6 hidden units, the result will be 31. So there are 31 input neurons in the input layer, and that is what you need to answer this question. Keep in mind that this data set is not the same as the homework 6 data sets. Your homework 6 answer will be different from the answer that is indicated in this video. Alright, so that is the best use of this results output here for the neural network. And let's look at the performances here. So we'll look at the this table. Now, where is my magnifier? So, because misclassification is the best selection criteria to be used, we'll look at the misclassification rate. And here, misclassification rate for the prediction is 0.41. and the difference between the training and validation set is not so high, indicating that overfitting has not occurred too much, if any, and it is a good news. And now we take a look at the overfitting chart. Before you even look at this chart, make sure that you have selected to use the preferred criteria to compare the models. Here, misclassification should be used instead of the default average square error that this chart always uses when it starts. Now, the misclassification rate performances that were shown in the upper table just now were shown for this model with this vertical line. It is at the training step, maybe 10. It's the 10th training step neural network model. And as you see, the model trained for 100 iterations, and the best model was in the 10th. That means the later 90 steps of the training have already made the model overfitting, and you see the blue line indicates that the training set error rate keeps reducing and reducing until it hits close to 0.35, and by that time, the difference between training and validation set misclassification rate is by 0.2, is by 0.1. So difference between 0.45 and 0.35, it's 0.1 difference. It's a huge difference in the training and validation set. That is clearly overfitting. And the optimal model that does not show too much of overfitting happens at the 10th iteration of the training step. So this is how you read this this graph. Now, with that said, neural network model has been trained fairly well, and so let me quickly do a decision trees here, and to quickly compare with the neural network model to see which one performs better. Now, decision trees is this. For decision trees, I will mostly keep the default setting here, but I need to change the selection criteria. I will not change the depth and branch count. I would change subtree assessment. I will make sure to use misclassification rate as a criteria, even though it means the same thing here without specifying the decision weights. And that is it. And before I train that, I will just complete the path by using the model comparison node to compare the two models. And I need to, for this model comparison node, I need to make sure that I choose the right comparison criteria. Model selection, selection statistic, misclassification rate, and we have to use validation set to compare them to be to be unbiased. Selection statistic is misclassification rate, and this one, let me change it to default because it's not applicable. So make sure you have selection statistics of misclassification rate, and selection table is the validation data set. Good. Now I can run the whole thing. Take a look at the model comparison results. And in this case, when the selection criteria is the validation misclassification rate, we see that the neural network model is slightly better than the decision trees model. It's only very slightly better than the decision trees or the best classification tree, but the neural network model is slightly advantageous in terms of the computation power. Okay. Now, one last thing I would like to talk about is the auto-neural. That some students might have found that there is a auto-neural model here somewhere. Let's see. It's auto-neural. So this auto-neural network, this doesn't mean that you didn't have to specify anything and the model will automatically choose the right specification for the network for you and train, and get the best results. That's not it. Auto neural network perform one and only one purpose. That is, when you have a new project and a new data set, and on which maybe the domain knowledge may even be obscured or be vague. In that case, you have no idea how many neurons should you use, and because neural networks have several other properties that you need to specify, and out of all the uncertainties, you don't know where to start. So auto neural network will try to search the space, the uncertainty space, the data space, to see roughly what number of hidden neurons might be appropriate or might be best to start with in your customized neural network model. So it will start from one hidden neuron and try a few things and move on to the second, move on to two hidden neurons in the hidden layer and try a few things and move on to the third until it finds that, oh, the model is overfitting badly, and it will stop and reverse back to tell you probably a preliminary number for the optimal number of hidden neurons in a hidden layer. So that's what it does. So that's why you see that in the specification here, number of hidden units to try, number of hidden units to begin the trial. It automatically says 1. It says 2, but you can try 1. And maximum iterations, maximum number of hidden neurons to try. Because it starts from 1 or 2 or a slow number and it stops at the highest number, and every iteration changes the number of hidden neurons by 1. You can specify tolerance, and this is how aggressive or how badly you can tolerate the model to be, training times. And you can try this tool to before you run the neural network models. If you have no idea what number should you put in the network, in the number of hidden neurons. But if you have a good idea, based on the size of the data set, based on your domain knowledge, you may feel free to ignore using this. It doesn't mean that you have to use it. And I would say you would never do this link, because this model trained here is a very crude model. It does not have the nuanced specifications compared to the fully connected neural network. This is more of an exploratory tool. With that said, this is the end of this the second part of neural network video. I hope you guys enjoyed it. Again, as we practice the work from home to help contain the virus spread, I think you and me, we will all become used to, hopefully very soon we'll be used to this way of working from home, and productivity should increase over time, because humans gradually will build up good habit and good routines in the process of work in the environment. This is actually what I study, IT habit. So as you build up healthy routines in a stable environment, you will over time, gradually get better and better in using the time and produce whatever you would like to produce from your work. Bye bye now.